We're going to explore how we find out if data blocks are missing on one of the QIC tape cartridge data formats that I've learned to read. We'll start with the, let's see here. We'll start with the Kennedy. I guess we need to start with the Kennedy. This is just the Kennedy 6400 format, or the 64XX format. This format has something called interblock gaps. Interblock gaps. And if you go to my page on that here, Kennedy 6450 tape drive data format, and look for the interblock gaps section, you can see the definition according to the manual for this particular hardware, exactly what the interblock gaps mean. The standard IBGs, or interblock gaps, between records or file marks written on the tape shall be a minimum of 1.2 inches. Now, all right, the standard gap from load point to the first record shall be 3 inches. Fine. Now, I'm not able to measure these gaps in distance. I am able to measure them in time, and I'm sure we could come up with some kind of formula that determines the distance on the tape from the time that it takes to read it at the speed it's being read in the machine. I don't feel the need to go that far, because what we're going to do here is we're going to basically compare the gaps between records, right, or blocks. And I'm going to use the term records and blocks interchangeably, because I think that's just terminology or nomenclature here. Because the real question is, well, is a data block really a record, or is a record a file, and a file can be a data block can have multiple files, or it can span data blocks, or whatever, so on and so forth. Let's not get too confused about that. So for the sake of this conversation or this demonstration, I'm just going to use data blocks and records as the same thing. Okay. So because this format does not count, because this format does not provide, let's see, what is it? The QIC 11 and QIC 24 provides a data block address where it identifies the number of the data block that it is on the track. And this doesn't do that. So when the blocks are written, they aren't numbered. You know, there's nothing that I can find that identifies we started track 0 at block 0. This is block 55. Nothing. So I have to count them sequentially. So the programs that I've written actually do that, and let's look into that right now. We will look at the data block bytes report for this particular format. And here is one of them from tape CC. And we're looking at track 0. The first block on that tape is 8192 bytes, followed by a file mark. And if you want to see exactly what these things look like and how I derive this, you might want to look more at this page right here, Kennedy 6450 or 6455 QIC tape drive format analysis on microtechM1.blogspot.com. I have another page for that here at QICreader.com, and there's a tab that says Kennedy 64XX format that links to that page. Okay. So we'll breeze through some of that, but I just want to show about the interblock timing that I've calculated. So here on the, I have a lot of files open, isn't that fun? All right, so here on the data block bytes report, which is the master report that my programs create that I use to diagnose pretty much everything, because it has all the information on each data block that I would want to analyze. The first block is 8,192 bytes. The second block is a file mark. The third block is 8,192 bytes. And the fourth block is 4,096 bytes. Okay, so what I'm doing here is my program actually counts the blocks sequentially. So in theory, if it missed reading a block that was really on the tape, the count could be off. And there's no other way to catch it other than to look deeply and look for potentially missed blocks. So I've written some programs that do exactly that. Now, because we have this concept of interblock timing, one of the many programs that I have that actually processes this data from data pulse timing all the way to output in bytes and files and such is a program that I have called the Datablock's counter. And this is the Kennedy version 3 of my program that I've written. So this is my code written in Lotus script, and it actually serves two purposes. A variation of this program when running on QIC 11 or QIC 24 data format actually gives me a count out and a comparison of the sequential blocks versus the number in the block address that the blocks identify themselves as. We can't do that because there's no block address section of this whatsoever. And I think I'm going to show you what I mean, because I've mentioned that now a couple of times. Let's go over here to the QIC 11 and QIC 24 format, and I'm going to show you what I mean by block address. Okay, block address. So let's look for, there's plenty of block address here. Block address, okay. So the block address, whether we're dealing with QIC 24 or QIC 11, they both consist of a 4-byte block address with a track number. No, this is QIC 24, excuse me. Block address. They both have block addresses. The question is how they manage the block addresses. QIC 11 and QIC 24 handle them differently. But QIC 11, but they both have a block number. So they actually sequentially number the blocks. How many bytes they use to track that block number differs between QIC 11 and QIC 24. But they both track the block number. QIC 11, it goes from 0 to 255 back to 0 again. And then QIC 24, there's more bytes in the address so that it doesn't have to reset after 255 because it runs out of space in the address block. The address space, whatever you want to call it. Okay, so block number. Block number, the first block on the tape shall be block 1, and subsequent blocks shall be numbered sequentially. The block number shall not reset at the end of the track. Now that's QIC 24, QIC 11 is different. The whole reason I'm explaining this to you is I want to say that this is not available. The block number does not exist. There's no such thing as a block number in the Datablock anatomy or the Datablock format on this enigmatic Kennedy tape format. Instead, we have a preamble, the data, an end mark, a CRC, and a postamble. There's no block address. And there's also, unlike QIC 11 and 24, which is just a continuous stream of data where a preamble and a poll, the preamble for one block is also the same as the postamble for the previous block. In this case, there's inter-record gaps or interblock gaps. We're going to analyze those interblock gaps right now. So this program does two things. For the Kennedy format, it gives me the interblock gap timing. And so we're dealing with the Kennedy format, so we're going to look at the interblock gap timing. So one of the things that I do is open this file here called interblock gap timing right here. Interblock gaps timing. So when I open this file, I believe I already have that open right here. This program actually has a parameter hard-coded into it. And that is the range. Anything below 0.070 seconds is considered too small of a gap. Anything higher than 0.078 is considered too high of a gap, and it will alert me on this report that there is something out of range. So let's show you what that looks like. Now, I just basically determined this by reading several of these tapes and figuring out what that optimum block gap is. And you can see this is a pretty narrow range. I mean, that's 8/100ths? Something like that. The math brain's turned off at the moment, so I apologize for that if I'm wrong about that particular detail. But let's look at the report. This is the report that this creates on track 0 of this particular tape. Now, we start out by noticing that the gap is high here between block 1 and 2. I don't know why it doesn't record block 1 in my report. That's probably a bad programming, because I'd really like it to give me the timing of block 1. It should have given me the timing of block 1 so it could show me the start point, which is right here. It should have put that in right here, just so I could make that determination. But anyway, what this basically does is it remembers this value, and then when it reads this value, it subtracts this value right here, 1.776 blah blah blah, from 2.12, and it comes up with a difference of 0.334. Well, this is higher than the 0.078, so it marks it as high. Now, this is actually expected because these interblock gaps or inter-record gaps are not as consistent as the documentation would lead you to believe. So what's happening here is there's differences, there's variations in this when we're dealing with file marks. Okay, so not only do we have blocks of varying size, where the first and the third blocks are 8,192 bytes, as opposed to the rest of them, which are 4,096 bytes, but also the gaps when they come to a file mark are different. Now, I know, even though this doesn't say it, block 2 is a file mark. And how do I know that? Well, my Datablock bytes report identifies that as a file mark. If you want to read more about how the file mark looks, just go to this page here, and I have an entire section on the file mark. I believe that's here's the file mark right here. This is how this works. Here's the documentation. I then show what that looks like, and I think I even find an omission in the documentation, which is that happens. But it all is explained right here. All right, so a file mark. So we have the first block, second block is a file mark. So the third block starts the first block of the next file. Okay, and in this case, this block is 8,192 bytes long. Fourth block, 4,096 bytes long. Okay, but let's look at the timing between the two. So what I've noticed is before a file mark, the gap is unusually long. It's actually a multiple. So if the ideal gap is 0.075, then what is this? What kind of multiple is this? We go here to the calculator. That's supposed to be a point. They did not get the decimal? Oh, well. Let's just go to a standard calculator. There we go. Divided by 0.074. Okay. Divided by 0.074. It's like 4.6 times the length that it should be. So it's noticeable. But this is actually consistent. Between the last block of a file and the file mark, we actually see this. The documentation doesn't say anything about it, but with the 2, 4, 6, 8 or more, with the at least 8, 9, with the 9 tapes that I have with this format, that is consistent throughout all those tapes. Okay, and then likewise, the gap between the file mark and the beginning of the first block of the next file is also high. Now, that's probably because we're not actually measuring the distance. We're measuring the distance from the end of one block to the end of another. That's how we measure this. So does that make sense? Yes, it does make sense, because I'm only measuring the ends of the blocks. So really what we have here is, I guess I misspoke. What we have here is a combination of the difference between the block, the gap between the end of the last block of a file and the file mark, as well as the fact that the block is twice as long as the other blocks. So I need to point that out, that there's some variation in my calculation here. But having said that, let's see here if I can recalculate. If I can recap my thoughts. this could be because this block is significantly shorter. A file mark block is only a few bytes in width, whereas the rest of these blocks are 4096. So the fact that this is almost twice as long as the rest of these could be because the file mark block is shorter. The point is that this finds the anomaly and points it out and says, hey, look at this. So what I do is I actually look at this visually. Here is the logic analyzer capture file for track 0, and I'm actually going to look up this time. So I'm going to find the file mark here at 2.12129 seconds. 2.12129. So let's find that here. 0 and 10, that's 2. Well, let's look for the 2. So we zoom in until the 2 becomes available. It's 2.12, 2.1, 2.12. Oh, there it is, right there. 2.121. Here is the file mark. That's what a file mark from this enigmatic Kennedy format looks like. And it's actually a very, very short block. Because when you compare this to the next block, look at how wide this block is. See that? It actually slowed down scrolling before it got to the end of it. So it is significantly shorter. Of course, if we zoom out too far, they all look like one block because the noise all runs together between the blocks. Anyway, where I was going with that, let me get back to 2.12129. 2.12, 2.12, 2.11. There it is, right there. Okay, so basically between here, I'm going to take the marker right here. I'm going to put marker 1 there, and then I'm going to find the beginning of the next block, which is right there. And I'm going to put marker 2 at the beginning of this. By the way, I'm just holding down I'm just hitting the 2 on the keyboard, and then moving the mouse until it snaps to one of the pulses, and then I click it and it locks it in position. That's how I use this logic analyzer user interface. Saleae Logic 1.1.15. Okay, so we're dealing with a timing gap here between 1 and 2 of 13.16.61 milliseconds. Okay, or 0.136177. That's exactly what we should see here. 0.13. No. Close. Very close. I'm going from the end to the beginning, not the beginning to the beginning. That accounts for that. When really I should be going from the end to the end. This is the end of this block, right here, to the end of the next block. See, I have to make this documentation because I get confused myself just when going through this, because it's just such a strange process. The point is, I'm looking for anything in here between 1 and 2 that might look like partial block or something that could be missing, and I don't see it. I see a nice clean preamble here for block sequence 3. This is a nice clean preamble for this format. Nothing wrong with that. Looks beautiful, reads beautifully. And then we scroll over here, and it usually becomes very obvious at this level because you get these white sections that really indicate, data. And I just read about there is really ideal to see this. We just don't see anything. This is noise. This is far spaced enough that I have identified this consistently as noise, and this is consistently what noise looks like on tapes when no data is actually being written. So visually, I have confirmed that there's nothing missing between those two. So let's go on and see if there are any more. So I'm going to do a text search here, and I'm going to search for these arrow things that I put here in this file that my program writes, and I find that there's some problems here between block 116 and 117, between block 118 and 119, and between block 119 and 120. Now, I'm not going to go into this except to say that my program already identified errors here. So what we have are blocks that are not complete in length. So block number 117 has already been identified as having an error and being too short, as well as block 119 has already been identified as having an error and being too short. But we can look at that and make sure that nothing else is missing in here. So let's look at that more deeply. So here I'm going to go to block 17 in my Datablock bytes report, the CRC verified version, and I'm going to find the error that it found. And here is, my other programs identified a problem with this block. It basically said the postamble isn't present. All of the end block measurements are messed up. And so Datablock contains unrecognizable characters at 7477 into the nibble count. And so with a 4096 byte block, we should expect 2 nibbles for every byte. So, there should be 8,192 nibbles. So 7747. Basically, it terminated the block at F. Did I do that wrong? There's like 445 bytes missing here in this. And the error really started right here. So, and I've already done error correction on this to determine exactly what happened, and I fixed it. There's other videos that I've provided on that and other sections on error correction on my site. But this is just about identifying missing blocks. So, because this block ends sooner than the rest of them, I would expect the gap between 117 and 118 to be just a little bit on the high side. So let's see if that's the case. The block between 117 and 118 to be a little bit on the high side. So what's happening here? Well, between 116 and 117, it's actually on the low side. So let's think about what that means. I think we need to look visually to see what's going on. So let's start with blocks 116. So we're going to go to 10.4335. So let's go back here, and we're going to go to 10 seconds, 0.4335. So now it's not 11. So the range here between 10 and 20, each of these means 11, 12, 13, 14. So it's 10 point something. So it's going to be between 10 and 11. So between this range right here. So between 10 and 11, and I'm looking at 10.4335. So 10.4, so between 0.4 and 0.5, 10.4, 3. Oh, let's see how that just becomes clear there. 10.4335. Okay. So, this is the end of block number 116. And everything looks good here. This is a good postamble. This may or may not be part of the postamble. If not, it's just noise. It certainly isn't extra data because it's right after the postamble, so I'm not worried about that. So I'm going to put the beginning of the gap to be right here. Okay. So now okay. My logic about my own program was wrong. I see what's happening. All right, let's go to the end of block 117 and I'll show you. 10.502559. This is actually too low. So it's the inverse of what I said. 10.502559. So let's go to 10. I can probably take you right there. 10.502. So here we are at 10.5, 10.50, 10.50, 10.5. This is, no, I can't take you there visually. This I'm going to have to really count. 10.502. 10.50. I'm too close here. 10.501, 10.502. So here we are. Nope, that's 10.5002. See how confusing this can be? Over here. That's probably it. 10.502. Now we're closer. And I think I'm beginning to see the data dropout right here. Because that does not look normal. And we zoom right in on it, we can see right where it is. So let's confirm 10.502.559. So where are we here? 10.502.550, 10.502.559. That is right here. So this has been identified as the end of this block. Well, the reason why is because there's a dropout in data. And it says, oh, the data ended. And my programs do enough cross-checking that they basically verify is this block valid or not. And the data ended, so the block, it stopped counting that as a block. My program did, and then it identified problems with it later in the process. Now I can see visually here that the rest of the block actually goes on, and the real end of the block is actually right there. That's the postamble, and so the block should, if this data dropout didn't happen right here, the block should be ending here. So what's happening is the block is ending too soon, so therefore the gap between blocks 116 and 117 is too low, ever so slightly too low, but notice it correctly identified it as a problem. So this program is doing exactly what I designed it to do, and it is alerting me to timing anomalies between the blocks. All right, so let's move on. I really want to understand what's going on here, so I'm actually going to go through all these anomalies just to make sure that they're all the same. So I believe I want to look between block 118 and 119 to see why this is high. Now I know that block 119 is an error, but let's see why this is high instead of low if it's the same kind of error. So let's go there now. And what do we have? All right, so I want to look for 10.57837. 10.57837. All right, so 10, let's get rid of 1 and 2. We'll reset those. 10.57, 10.6, right? So maybe I was there already. We're still at 10.50. 10.51, 2, 3, 4, 5, 6, 7. That probably has something to do with that. 10.57, 8. There we go. 10.57837. Right there. What we've identified is 10.57837. This is the end of this block right here. So it identifies, and that's quite of a wide, really wide data pulse there, but this was a really clean postamble, and then there was this nice gap of silence before the next pulse. And the way my programs work is they find the next pulse. It measures the timing between the pulses. So it just kept waiting for the next pulse, and it found that the next pulse was way out here, way out of range. So that says, that's where this block ends. That's where I'm going to stop considering it a valid block. And that's all correct, right? That's in the scope of things here. That timing is not significant. So that's where block 118 ends. Now let's look at where block 119 ends and see why that's high. Block 119 ends at 10.66044. So let's go to 10.60044. All right, now I'm visually just going to do this here and see, because this looks like a normal block. What is it? 10.66044? 10.6. Huh. Look at this, I might have found one. No, that's 10.7. What's going on here? I know what's going on. It's right here. 10.66. Might be that. Is that it? Yes. 10.66044. 10.660449, which is right here. 10.660449. Okay, so right there is where it ends this block. So the distance between the end of this block and the end of this block should be, oh, look at this. That we did find a missing block here. This is interesting. This is very interesting. Okay, so here's what I mean. And this is the value in this process. Whether this is a real or not a real valid block, I don't know. But this block, the block that I'm counting as block 119, clearly starts right here. That's a nice preamble and data block marker, and there's the data. Okay. The block ends prematurely, which is right here. We have a data dropout, a gap that's too wide, and so that's what's going on there. So the block ends prematurely. So what we have then is this block isn't being counted. Why is this block not being counted? Well, I'll tell you why this block isn't being counted. Because there's no preamble. Look at that. There is no preamble whatsoever. And so we have data that just starts in with no preamble. And so this, the process just did its job. I found a missing block. And the missing block is basically at 118.5. So I'm going to add that to my report here. At 118.5. So the program did exactly what I designed it to do. And it found a missing block. Right there. So let's see if we can read that missing block and see what's going on with that. All right. So, good job, program. Now, we'll finish here, and now I'm going to identify block 119 here. And I'm going to say that I'm going to say that this is high because block 119 ends prematurely, and the distance between block 119 and 120 would be too high because block 119 ends prematurely, and therefore the end of block 119 to the end of block 120 is too wide. I'm not going to. I know that's the case, so I'm not going to demonstrate that really deeply. But I'll just show you what I see here on the data block bytes report. Block 117 is fine. Block 118 is fine. Block 118.5 is missing because we needed to go through this process to detect that it existed. And here's block 119. Block 119 is too short. I can tell just by looking at the block sequence here that we had a bitwise shift, and so there was something wrong. Basically, the program said, hey, there's a big problem here at 322 nibbles into this block, and so you've got a problem. And so that's why it puts these warnings in here. And so when my further subsequent programs go through and read this file, it identifies this as a bad block. But the deeper analysis we've just done here, finding a missing block, is really key. So I'm going to go through my I'm going to read that partial block. The way I'm going to do that is I'm going to go through my error correction process method 2 here, the bad block reassembly. And if you want to learn more about that, just go to QICreader.com, click on error correction, and go to the method 2 section and read up on how I actually recreate a block from the back end. And well, I guess that's not an or. It is I recreate the block from the back end, or from an error point forward, using some very innovative techniques. And that's how I'm going to figure out at least what the partial block says. So give me a moment and I will do that now. Incidentally, I think I had already identified that missing block, because in this Kennedy format, one of my programs spits out a report called the Potential Data Block Without Preamble report. And all that does is it basically gives me the block addresses of every known block that is good. But then if it starts to see data where the preamble hasn't identified a block has started, then it basically gives me the data pulses that look like they could be data pulses because they're within the correct range. And there's so many consecutive ones. I don't know, 50 consecutive data. I think I designed it so that 50 consecutive valid data pulses constitute, which don't follow up a preamble, constitute a potential data block without a preamble. And so it has identified one here at 10.502817. And the question is, I think that's exactly where missing block has been found using this other process. And I think it has right here. So I've already have another report that alerted me to this. But you see how I've created multiple ways to ensure that we have the right data, that we're not missing blocks when we're dealing with non-counted blocks with inner block gaps or inner record gaps, where something could be in between and you wouldn't know unless you were really specifically looking for anything that even smelled like a block. It's exactly what we've done here, and I just wanted to point out that was another portion in my system that identified this, the potential data block without preamble report. And let's see, which one of my programs creates that? Let's see. I believe it is the, I think it's the first one. I think it's the Kennedy format data block strings. Yes. The decoding to data block strings. This one specifically for the Kennedy 6450 format. It happens to be version 3 of what I've written, but here's the program that creates that file. So now we know which step of the process that program runs. And by the way, if you're interested in seeing the whole QICreader.com, if you're interested in seeing the whole process for bytes translating from data pulses, what do I want to say here? From the logic capture, yes, sorry, I'm stumbling over my words because there's so many complications in this thing. The logic capture device. So the logic capture files to actually getting to bytes. You click on bytes translation here at the top of QICreader.com, and you will see that I have an overview of all the stages. And so I'm just going to point out right now that it is stage 3. That program that I just showed you here, the potential data block without preamble report, is created as a part of the stage 3, the decoding data blocks to strings program. And that's where I just showed you that particular code. Okay, so let's move on to seeing exactly what this block says.